Hi, everyone. My name is Brandon Rodriguez. Thank you so much for joining us today for our next installment of Teaching Space. And I work at the Jet Propulsion Lab at Pasadena, California, a site of NASA in the Education Department. And if you've never seen some of these series before, it's a really awesome opportunity for us to kind of explore with some subject matter experts from around NASA on the really wild careers and scientific progress that we're making. Today we're joined by Paul Chodas, who works at the Center for Near-Earth Object Studies. And this is going to be a really cool talk because this is something that is not so distant to all of us. When we talk about things like, landing on Mars, this is something that, you might not have seen yourself, right? Mars is something like, it's so far away from us. Versus when we look at things like comets or asteroids, these are things you might have actually seen yourself. You might have looked up in the sky and seen. So I'm really excited to hear from Paul today. Before I turn it over to him, let me remind you that we'll begin with a little talk from him. Really excited to see that presentation before we take some of your questions live. So if you have any questions to submit, please check out the Teaching Space page, submit your Q&A, vote for ones you like, and we'll make sure to address those. After that, we'll do a quick rundown of the types of activities that JPL Education offers so that you too can kind of recreate this science yourself. How can you actually take what we learned today to your classroom, to your homes, and etc. So let me dive right in and turn it over to Paul. Thank you so much for joining us today.
Thanks for inviting me, Brandon. I'm going to give a talk about asteroids and comets, and if you're looking at the title slide here, I drew some of the orbits of just a few of them, and you can see the Earth's orbit there as the bright circle, and the orbit of Jupiter is the big circle, and there's a lot of them. So there's a lot to talk about, and I hope to educate you a little bit, tell you about what's going on with asteroids and comets, and first of all, what they are, where they are, and then maybe why we should be tracking them, and if they can come close to the Earth. Next slide, please. Slide 2. So where do asteroids and comets come from? Well, basically, our solar system formed about 4.5 billion years ago when it was where there was a large molecular cloud of gas and dust, which was collapsing. And most of the gas and dust collapsed to form the sun in the center, but most of the rest formed the planets and coalesced into those. But there was still leftover stuff and gas and dust, and that formed the asteroids and comets. Now, the objects which form far from the sun still had the frozen gases in them, and they became the comets. And the objects that kind of coalesced and they were closer to the sun, which is hotter, the gases weren't there, and they became the asteroids. So that's basically where they all came from. Slide 3, please. So what are they? They're basically, comets and asteroids are small objects, and they're orbiting the sun. Okay, they're not that generally near the Earth. They're generally far away, and that means on the sky they move pretty slowly from day to day. It's like planets. Planets move pretty slowly from day to day on the sky. Now, an object is a comet if it appears fuzzy or has a tail. Otherwise, it's just a point of light on the sky. It's an asteroid. We never see these things as bodies. We never see them close up. They're just points of light, really. 99% of the small solar system bodies are asteroids, so the comets are in the minority. Now, some people ask about meteors, and those are small objects that are burning up in the atmosphere. Okay, so that's something really close, and it happens really fast as a small rock or pebble burns up in the atmosphere. And I'm not going to be talking about meteors. I'm talking about stuff orbiting the sun. At the bottom here, you see Comet Hale-Bopp back in 1996. That was one of the great comets, and you could just go outside in your front yard, and even if there were streetlights, and you could see that comet hanging over your house. It was really quite bright, even though it was far away. And on the right there is a close-up of one of the near-Earth asteroids, and they're just rocky bodies. Slide 4, please. So, okay, now where are they? I drew this specially for today. I'm showing where all the major large comets and asteroids are in the solar system as of today. So there's 33,000 of them on this diagram. That's a lot. I cut it off at 3 miles across. So when I say large, I mean something that's 3 miles across or larger. Most of them are in the main belt. They're orbiting between the orbits of Mars and Jupiter. And the largest of them is called Ceres. It's 600 miles across. But their orbits are pretty circular. They stay more or less in the main belt. There's very few of them that come into the inner solar system. But what about the smaller? Oh, I should point out the Trojans. So there's some asteroids that follow the orbit of Jupiter. And they're like 60 degrees ahead and 6 degrees behind. So that's kind of really, really a special group. And I've shown comets here as these little white V's. They're scattered all over the place. The asteroids are generally in the same plane as the planets. But I just plotted the big asteroids. What about smaller ones? And how many are there? Well, there's actually over 1 million asteroids and comets in the solar system, and we keep track of them all. But there's a lot of them, and because as you go to smaller sizes, there are more and more of them. Okay, so it's 33,000 that are larger than 3 miles across. But if you go to smaller sizes, you just get hundreds of thousands of objects. Now, what about them coming close to the Earth? Some of them do, and on slide 5, I have a close-up of one of them. This is a near-Earth asteroid called Bennu, and it was visited by NASA's OSIRIS-REx spacecraft. Took this great picture of it. It's about 550 meters across. I'm going to give distances in meters and feet, 1,800 feet across. That's a near-Earth object, and it's a pretty big one. And if you go to the next slide, you see a close-up of what it looks like when that spacecraft actually touched the asteroid and got some samples. So you're seeing it really up close here. That circular sampling device is about 1 foot across, okay? And so you're seeing all the little rocks and pieces of that asteroid. That's what an asteroid looks like close up. Now, let's talk about comets. That's slide 7. Halley's Comet is my favorite because that's what I started working on when I came to JPL. It's the most famous comet. It's been seen throughout history. The old Chinese saw it in 240 BC, and Babylonians saw it, and the Anglo-Saxons saw it and wove them into tapestries in 1066. Halley's Comet has an orbital period of around 76 years, so you get a chance to see it once, basically, in your lifetime, and very few people see it more than once. So it came by in 1986, and I was fortunate enough to work at JPL, and we plotted the orbit of Halley's Comet because astronomers wanted to know where it would be exactly, and there was an armada of spacecraft that were going to visit it. And in the lower right there, you see a picture of the nucleus of the comet, Halley's Comet. Now, while the tails of comets can be millions of miles long with the gas and the dust coming off, the actual solid piece, which we call the nucleus, is small. And in this case, it's like 9 miles across, and that's a close-up of it. And you can see all the jets of the gases boiling off as it gets near the sun. They heat up, and they shoot out the dust and gas, and that's what produces the tail and the coma and all of that stuff that goes millions of miles away. Slide 8, please. Now, I was always interested in orbits, so I'm going to say a few words about this slide because I'm into orbits. You know, the early civilizations like the Greeks and Romans, they thought that the Earth was the center of the universe and everything revolved around us. Well, Copernicus in the 1500s, he realized that no, it's the sun at the center, and everything, he said, revolved around the sun. And that's more or less right. He thought they were moving in circles, which isn't quite right, but everyone assumed the orbits were all circular. Now, Kepler, in the early 1600s, realized that planetary orbits were ellipses, not circles, and with the sun at one of the focuses. And that was his first law of planetary motion. You can look it up, Kepler's laws of planetary motion. The second law talked about how fast planets travel when they go on their orbits. And the third law gives a little math relationship between the size of the orbit and the orbital period. Now, Halley's Comet here is that big, long blue ellipse. And it takes 76 years to go around, which is about right for something, an orbit of about that size. Now, Kepler didn't realize that his laws applied to everything orbiting the sun, not just planets. He just gave the laws for planets, but applies to Halley's Comet equally well. And I want to say one last thing about orbits. They are more or less constant in time. So if I plotted this, 10 years ago, Halley's Comet would be the orbit would be the same, but the position of the comet on the orbit would be a little different. So that's really, it's the position of the asteroid on the orbit that changes, but more or less, orbits stay constant in time. Okay, number 9, slide 9. The comets are weird. You get all kinds of shapes and sizes, and this one is Comet 67P. We number them. Churyumov-Gerasimenko, we just call it CG for short. And it was visited by European Space Agency's Rosetta spacecraft. Weird shape, it's about 4 miles end to end. You might ask, well, how are comets named? And they're named after the discoverers. So Churyumov and Gerasimenko discovered this comet in 1969, so it was known for quite a while. But whoever discovers a comet and announces it first to the International Astronomical Union gets their name on the comet. So that's where the names come from. Halley was an exception. Halley was the mathematician who figured out that comet's orbit. Next, please, slide 10. There's another weird comet that I worked on a lot in the 1990s, and that one was called Shoemaker-Levy 9, discovered by Gene Shoemaker and David Levy. This comet was in orbit around Jupiter, which is totally weird and a totally unusual case. And furthermore, it consisted of like 21 different fragments. We gave them names, you know, fragment A on the left and S there, and fragment G, I think, was one of the bigger ones. And our orbit calculations we did for this one said that those fragments would all impact Jupiter in a few months, basically almost a year. So that was really exciting. And I got to do all the predictions of where and when that comet would hit Jupiter in the year 1994. Slide 11 shows one of the big impacts of the fragment G, which we think was like between 200 and 1,000 meters in size. You know, that's we really don't know the size of the nucleus because it was far away. But the impact energy was megatons, millions of megatons. And furthermore, it left a big black mark on Jupiter. And that was kind of cool for me because, yeah, you know, we had done all the math and the orbit predictions months ahead of time. And we were pretty sure that it was going to hit there on the limb and actually slightly around on the far side and at that latitude. And sure enough, that's where it hit. And it was such a big black mark on Jupiter that you could go out even in a little telescope and look at Jupiter and you could see the black marks that those fragments left on Jupiter. So I guess that just kind of indicates, you know, the math, it all worked and we could predict that ahead of time. That's why orbits are cool. You can predict them, where things are going and make predictions like this. Slide 12 now moves the focus to near Earth objects. And I'm not going to go through all the words on this, just to kind of give you a general idea of how we define those. Near Earth objects are objects that basically, whose orbits bring them into the inner solar system, kind of close to the Earth. And that's the blue region in this diagram. If any asteroid or comet could come within that distance of the sun, then we call it a near Earth object. And I'll in a later slide tell you how many there are of those. Now there's another thing I'm going to be talking about, potentially hazardous objects, and that's shown kind of with that red torus around the Earth's orbit. That's basically a very short distance, about 5 million miles actually, around the Earth's orbit. And if an asteroid or comet orbit comes within that distance of the Earth's orbit, we call it potentially hazardous, even if it's not necessarily going to be predicted to hit the planet or anything like that. It's just the fact that the orbits come close. And I'll be showing you and talking a little bit about potentially hazardous objects as well. And Bennu is one of those. You can see with the dotted line. It's a potentially hazardous object. In fact, it's probably one of the most hazardous objects in our catalog. Slide 13 is my plot of where the potentially hazardous objects are today. Okay, and now those are all those dots. There's actually 2,180 dots here. You can see they're kind of scattered. And so you'd say, well, they're not near the Earth. Are they really hazardous? Well, if you go to the next slide, those are the orbits of all of those nearly 2,200 asteroids. And you can see they get really close to the Earth's orbit by definition. That's what a definition is of a potentially hazardous asteroid. So we want to keep really close tabs on those orbits. They don't necessarily have a chance of impacting Earth, but we've got to keep tracking them and make sure we know their orbits well enough to make accurate predictions into the future in case there's a chance that any one of these might hit the Earth's orbit. There's also, you know, these orbits go out of the plane of this diagram, so there's it's not quite as busy around the Earth's orbit as this diagram indicates. Okay, next, slide 15. Does stuff hit the Earth? Well, yes. I mean, you can go out on any dark night and in a dark sky, you can see meteors. And those are little pebbles or rocks hitting the Earth's atmosphere and burning up, they only last maybe a few seconds as they flash through the atmosphere. Sometimes you have meteor showers. Those come from comets where there's a lot of debris and dust that's kind of all together and coming from the same direction. In general, 100 tons of interplanetary material impacts the Earth every day. So most of it is dust, but sometimes you get larger pieces, and sometimes meteorites reach the ground. Slide 18 is an interesting story. Back in 1992, we had a 17-year-old girl here whose family gave her this kind of old junker car. And so she suddenly heard and it's parked in her driveway, and she heard a big bang on a Friday night, and she wasn't sure what it was. It was a big noise. She went out and checked the car, and something had happened to her car. She thought it had been hit by something. Maybe some guy came and hit it with a baseball bat. Well, no, it turns out it got hit by a meteorite. And it was a Friday night, and there was a lot of video from people filming their football games, high school football games or whatever, in Peekskill, New York, and in fact across the eastern seaboard of the U.S. that saw this meteor come into the atmosphere and burn up. And all that was left, if we go to slide 17, was this meteorite, and that's like a foot, more than a foot in end to end. 75 pounds is what hit her car. So she had to kind of explain to her parents, no, I didn't crash into anything. It was a space rock that hit my car. She made some profit from this. So she sold the meteorite for $50,000, and she sold the car for $25,000 because it's such a rare story, and they're both in museums now. So you know what? If you're lucky, or maybe unlucky, I don't know. She didn't get hit herself, but her car became a souvenir of, a tiny asteroid that hit the Earth. We didn't see this one coming. This was too small. We didn't see this one on slide 18. Now, this was a bigger one. In 2013, over Chelyabinsk, Russia, there was a massive fireball, really bright, 20 times brighter than the sun. It just lit up the whole sky. I guess this happened at around sunrise. And what I've done is shown the whole trajectory of this really, really bright meteor through the sky and its altitude. So it started at like 90 kilometers altitude, 30 kilometers is where most of it burned up, and 25 kilometers, there's pieces still going through. That was a 500 kiloton energy explosion, basically, and it shattered a lot of windows and damaged some doors and stuff like that. It was caused by what we think is a 20-meter asteroid, okay? Now, that's a rare case. We don't think that happens very often, maybe once every 50 years or so. And this was completely unexpected. We didn't see this one coming. It was coming from the direction of the sun, which is off to the left in this. If you go to the next slide, which is 19, you see where it landed. It landed in a frozen lake, and it put this nice circular hole in the ice. This is February in Russia here. And later on, a few months later, they dredged up the bottom and they found the meteorite, which is like 3 feet in size, and there it is. That's all that was left from a 20-meter asteroid. All the rest was pulverized into dust into the atmosphere. So that's what happens when we have a larger event. Slide 20 is a historical impact, again in Russia, this one in Siberia. And that was, we think, about a 40-meter object that flattened like 2,000 square kilometers of trees. We don't know of anybody who died, but there might have been a few remote people living in that area. And we think that's even rarer. That something of that size hits every few hundred years. Now here I'm going to larger and larger sizes, and they hit less frequently because there are fewer of them. So there's kind of a rule here. If you go to small stuff, there's a lot of it, and it hits more frequently. If you go to bigger stuff, and now this is 40 meters, it hits maybe once every few hundred years, on average. Slide 21 is a even slightly bigger asteroid made out of mostly metal that hit in Arizona 50,000 years ago and left this huge crater. That is a rarer event, that energy. That happens maybe once every 10,000 years or so. We hope that doesn't happen while we're around, but that's what could happen if the asteroid is made out of solid metal. Slide 22 is the one you probably all heard of, which is the asteroid that killed off the dinosaurs 66 million years ago. A really large asteroid, about 10 kilometers, 6 miles across, impacted the Earth. And where it impacted is just north of the Yucatan Peninsula. So that's like in Mexico, Gulf of Mexico, coastline there. That was large enough that it threw up all kinds of debris and dust into the atmosphere, which clouded the atmosphere for a year or more. And there was a lot of, and heated the atmosphere too. So there was a lot of fires around the world. It left a lot of soot layers all around the world. And in fact, you may have heard iridium. Iridium is an element that is common in extraterrestrial asteroids. And it left a layer of iridium pretty well all around the world. That is the evidence that what happened was a impact of something from space. So that you'll be pleased to know that a 10-kilometer asteroid does not hit very often, maybe every 100 million years. And furthermore, we're tracking all of the asteroids that size. They're not very many. And we know that there's no possibility of anything like that impacting within millennia. Slide number 23 talks about what could we do about it, because things can hit the Earth, and we don't want this to happen randomly. We'd like to actually keep an eye on these. So we have search programs. NASA has funded search programs, and along the bottom of this slide, you see some of the large telescopes that are searching the sky every dark night, looking for new asteroids and trying to find as many of them as possible. In fact, Congress has directed NASA to find 90% of the near-Earth objects that are greater than 140 meters, which is 460 feet in size, okay? So because that's really a hazardous size that could cause regional damage if it should hit the Earth. And we want to track them, find them, and then maybe we could do something about it if we could identify that as a possibility. This slide just shows kind of what an asteroid looks like on the sky. It moves pretty slowly, but over the course of an hour or so, we take like 3 or 4 images of the sky, and these stars are all basically the same, but there's something that's moving across the sky, and that's about an hour across. Now, you have to ignore all of the noisy stuff in the picture, because this is, we're really kind of stretching the photographs here. But we see that asteroid, and that's a near-Earth asteroid, and that's what it looks like, and that's how they're discovered. We have computers that search all the images that all these telescopes take and look for the objects that move and match them up to known objects. And if it's not a known object, then it's a new discovery. And nowadays we're getting like about a dozen new discoveries every night, and they flood into our computers, and we compute the orbits and trajectories for all of them. I'm going to go a little faster here. Slide 25 shows like a plot of the number of near-Earth asteroids discovered over time. On the horizontal axis is like the date of when it was discovered. And if you look on the right-hand side there, you see like the current numbers, well, as of early this week, 26,000 near-Earth asteroids is our total so far. And the discovery rate is like 2,000 per year. So we're finding lots of them basically every dark night. That's really going up fast. It's the orange plot, which is for 140 meters and larger, and that's what is more. Those are more hazardous, and we've reached almost 10,000 on that scale. And the large ones that could cause extinction level events, that's 1 kilometer and larger. We've reached about 890 of those, and we're not finding many more of those. We think we've gotten about 95% of that population. Now, I don't have time to explain it, but someone might ask, how do we know what the total population is if we haven't discovered them all yet? That's a good question for follow-up. Our group computes orbits for all of these. And when I started, there was, not very many. So we were doing things manually. But over the years, our group has grown. We have a large, several people who automated the whole process. And as I say, we're getting like dozens of a dozen asteroids every night, new asteroids, plus the old ones. We want to keep tracking those as well. The next slide, 26, is our homepage. If anybody you want to learn more, you can go to the CNEOS homepage. The URL is at the top there. I've highlighted in yellow what our main mission is. We are the center, NASA Center for Computing Asteroid Orbit and Comet Orbits. and computing their odds of hitting the sun. And I've also circled in red some of the key, the most important things you can do on our navigation bar and learn about close approaches, impact risk, and that kind of stuff. Next slide is an example. One of those pages is the close approach page. This is our continually updated list of upcoming close approaches. And I've circled in red here. This was what it was last week. And we had 8 close approaches in the course of just 6 days. So on the left there, you can see the names of those objects. And you might see that they're 2020, almost all of them are 2021 something. And we can talk about in the question period how we name these asteroids. The one in yellow is a return of an old one that's coming back. So that one doesn't count. But there's like 7 brand new asteroids just discovered, you know, in the course of a few days. And these make it into the news media. News media really likes visiting this table, and we get stories about that. The one there, I've circled on the right, is as large as the Eiffel Tower, and it's coming by, you know, it was coming by on June 1st, so that we got stories about that. You can click on the middle there, there's a brief tutorial. You could click and learn a little bit more about how we make this table, but these are all our computations. We're doing all the math here, because all the orbits and close approach computations are done here at JPL. The next slide I won't spend much time on, but it's slide 28. It's the list of objects that have a small chance of impacting the Earth. And when I say really small. On the left is the asteroid name or designation. In the middle is the impact probability. And on the right is the size. Now, the bottom line, and I won't go into this, but the bottom line of our analysis of what could hit the Earth is that it's either the chance of impact is really, really small, or very far in the future for a couple of these, or the object itself is really, really, really small. I mean, some of these are down at 13 meters in size. This is in kilometers, so that, you know, 2009 JF1 is 13 meters in size. So, so I just want to emphasize, our group keeps track of all the asteroids, and we make these predictions of whether any of them can hit the Earth. As we continue to observe these asteroids, by the way, the probabilities will change. So as we get more data on an asteroid, those probabilities will change. And in almost all cases, the probability will go to 0, we expect. I would note that Bennu there is a really special case. We can talk about Bennu in the question period if you'd like. But there have been a few small asteroids discovered that really did hit the Earth. Now, these were very small asteroids. And the next slide, slide 29, shows one of them, 2008 TC3 is the name of it. It hit the desert, Nubian desert in Sudan in October 2008, and was discovered on the last day because it's very small, and small asteroids you cannot see very far when they're very far from the Earth. They have to be close. So we did all the predictions, and we got the impact time pretty accurate, and that line going through on the upper map shows the ground track, and the red dots show where the meteorites were found. So we predicted where to look for the meteorites, and there they were, nice black meteorites on a kind of light desert floor. My last slide is 30. We also do asteroid impact scenarios, hypothetical scenarios. So we simulate large asteroids, largish meaning, you know, maybe 300 feet across or something like that. And then we simulate, well, let's say we discovered this one 8 years before it could hit. You know, is 8 years enough time, enough warning, so we could do something about it? And then we go and use all of our tools to, first of all, predict where it might hit. And that red line shows where, in this case, for this hypothetical asteroid, where it might hit, and it went across the US and some cities like Denver and New York City. Well, if we have 8 years of warning, what could we do? There's many different possibilities for deflecting asteroids, but you really need to find them with enough warning time. And 8 years, we think, would be enough time to deflect the asteroid. The easiest way to deflect it is by sending up a spacecraft to hit it years ahead. And we simulated doing that, and we felt that we could deflect an asteroid of this size. So we can, in the question period, talk more about deflection missions like that. There's one coming up called DART, the Double Asteroid Redirection Test. That's coming up. It's going to be launched later this year and in next year. it will actually try to deflect the moon of an asteroid. So that's an actual mission that's going to demonstrate the concept of deflecting an asteroid. And I'll stop there, Brandon.
Thanks so much. I mean, this is so interesting. These are, like I said in the top of the, these are the kind of things that we all do get to think about. This is accessible to us. And we have a ton of great questions that came in during your talk, and you've accurately predicted the most popular one, which is, tell us a little bit more about DART. Talk a little bit about is how can we actually solve a problem, again, within the understanding that statistically we are generally very safe, and you guys have mapped this out well. But in this kind of Hollywood scenario, I'm assuming the plan is not Armageddon. We're not going to have Aerosmith sing us a song and send some people up there. What is DART, and what could we possibly do?
Yeah, DART is the mission that will demonstrate the idea of ramming a small asteroid. In this case, it's the moon of an asteroid, and seeing if we can measure the change in the velocity of the asteroid. And that's all you have to do. You really only need to hit it with a moderate-sized spacecraft, enough to change its velocity by maybe a centimeter per second. I mean that's a really small change. But if you do that with enough time, and I'm saying years, if we do it several years before it could hit the Earth, if you change its velocity by a centimeter or 2 centimeters per second, something like that, really small, then that's going to be enough. And over time, then the new trajectory will miss the Earth. So you've successfully deflected the asteroid off the Earth. Now, for DART, which again is launching this fall, that is not going to an asteroid that could hit the Earth. Okay, so it's not going to change and it's not going to really even change the orbit of the asteroid very much. What they're doing is hitting the moon of an asteroid, and we're measuring the period of that asteroid moon, how long it takes to go around. And if we change its velocity, then that period will change, and we can measure that from the Earth, and then so we can prove the fact that that the deflection was successful. The spacecraft itself is, of course, destroyed when it hits the asteroid. So you have to kind of prove that you are successful by observing it from the ground. There will be another mission that goes and visits that asteroid several years from now and gets more data on how the orbit changed.
Yeah, that actually lends into a really great question that's been asked a couple of ways, which is, you talked about the why, but we haven't heard much about the how. So for an audience that may not have a lot of expertise in this area, how is it that you're able to track this with such accuracy? Considering the number of objects out there, a night of telescope is not a lot. So how is that you've been able to construct these models?
It's because astronomers with these large telescopes are observing sky every dark night. In fact, one of those telescopes I showed earlier observes the whole sky every dark night, and that's really tough. You have to have a wide field camera, and you're taking pictures, and you have to take 4 pictures basically of every part of the sky if you want to see something change over there. So they're taking a lot of very wide field pictures of the sky. So what we have, what are the inputs to us are the coordinates of where the asteroid was at each moment in time. So we know the time of the picture, and we know where it was on the sky, and we get like the latitude, longitude, and we feed that into our computers. And the more points we have, the better. In other words, it's like latitude, longitude points, and we build that up with time. And because, thanks to Kepler and Newton, the equations that govern, the predictability of asteroids orbiting the sun are really, really elegant and very precise. So we can actually, in our models, fit something over decades of these observations. They all fit to a single orbit. So we find the orbit that fits all of the data, maybe even decades of data, and fits every one of those coordinates as best as possible. And that's how, and the longer we observe an asteroid, the more accurate. It's kind of like fitting points on a piece of paper. And if the points are close together, well, there's a lot of different possible angles for a line. But if the points are far apart, that line has to be at a certain angle to fit them. And that's basically what we're doing with our orbit determination.
Awesome, awesome. Kind of in a similar line, you mentioned earlier that some things were too small to be detected. What are the detection limits?
Well, in our catalog, we have asteroids as small as like 1 meter in size. So the answer is how bright they are, not how large they are. So if the asteroid comes close enough to the Earth, then it's going to get brighter. And so, if it doesn't come very close at all, then a small object, let's say an object that's 5 meters across, 15 feet, something like that. We could detect nowadays, we can detect that with our best cameras, can detect that at like 2-3 times the distance of the moon, something like that. So it has to get that close. And now if it doesn't come that close, then we're not going to see something that's of, just a few meters across. So it depends on the size of the asteroid. And it also depends on its brightness, surface brightness. Some of them are dark. I showed pictures of Osiris-Rex, and Bennu. And Bennu is a really dark asteroid, and you can see that the rocks and stuff is really dark. And so that one, if you had an asteroid made out of that stuff, then it would have to come closer to get bright enough to be visible in our camera. So the answer depends on how bright it gets.
Similarly, talking about brightness and you mentioned some of the materials earlier that a rocky one had done so much damage, or a metallic one had done certain damage. Is there a known kind of distribution of which ones are rocky, metallic, or both?
That's another good question. Yeah, the composition of the asteroid makes a difference, and the spectrum, which could be as simple as just the various colors at different color bands in filters, or a more detailed spectrum of the asteroid in a large telescope. You get like how bright it is in each wavelength, and the asteroids kind of group themselves into types based on the features of the spectrum. And that's basically because we think of composition. There's different mineral types in some of these asteroids, and then the composition is related to the density, and the makeup. So something like Bennu is really light, very dark, and it's very carbonaceous and very light, so it's not very dense. There's rockier ones that are brighter, and they have a different spectrum. So from the ground, we can kind of group them roughly into different spectral classes, and that gives a clue and based on composition, and we kind of have a clue based on the spacecraft missions that did measure the densities. We kind of have a different density for each class. But the best way to measure an asteroid size, mass, basically, and density would be to actually have a mission. So that's if you really want to know it accurately. And for one of these scenarios, or something's really headed to the Earth and you want to deflect it, you want to know the mass, because when you run into it, it's a momentum transfer, and then how much deflection, the number of centimeters per second depends on the mass, which you don't know. So you really do need to study and characterize the asteroids and kind of get an idea of which class they're in, and that gives you a clue as to the density. But then sending a mission would help best.
I have just 2 more questions for you. One I really appreciate. It's a special, a little niche, but it's an idea I'd never thought about, which is, have we ever observed a comet that has kind of expended all its volatiles? Have we ever been able to see a comet effectively, dry up, if you will?
Well, that's a great question, because orbits change, especially comet orbits change. And so maybe they will evolve to be closer to the sun, and eventually all of these frozen gases will sublimate, and the gases will be driven away, and then you're kind of left with a dead comet. And there are some asteroids that appear to be, we think are dead comets. You can kind of sometimes tell from the orbit. Asteroid Phaethon, for example, is an asteroid that's kind of distributing a lot of debris. So we think that maybe that's kind of the loose debris left over from what used to be, which used to be a comet. So yeah, so there are some dead, what we think are dead comets out there. I think that hopefully that answers the question. It's a wild menagerie out there of all kinds of things. And I would add that comets are tough because when they, emit gases, that pushes the comet around, which makes it's computing the orbit a little trickier. That actually can push it along its orbit. So it's not just gravity that, we're using gravity mostly to model our really accurate orbits, but for comets, we have to account for this outgassing, from the jets, and that's a little bit more difficult. There's one other thing for asteroids: they heat up, and for smaller ones, you can actually detect how much recoil there is when the asteroid, the photons of the heat coming off the asteroid actually push the asteroid around a little bit. And for things like Bennu and asteroid Apophis, that's a good one to talk about. We can actually measure this thermal effect on the orbit, which is, non-gravitational. So we have to keep track of that as well.
Wow. Well, last question for you. A little bit of a two-parter. Is there any kind of opportunity or organization that young people could kind of have a citizen science role in this field? Or if not, then, what should they be pursuing to kind of be where you are now?
As far as discovery, it used to be that amateurs could contribute to discovery of asteroids, but now it's been kind of taken over by the really big telescopes that are going to fainter and fainter magnitudes. So amateur astronomers have less of a role in discovery, but there's still follow-up, and there is still a surprisingly large group of really capable professional or amateur astronomers who have their own telescopes in their backyard, and they are measuring positions of asteroids after they've been discovered. And we need those positions to make our predictions. In some cases, for example, we want to observe an asteroid with radar, and to point the radar, we need a really accurate orbit to send the pulses to the right place. And in some cases, we don't have an accurate enough orbit, and so we'll call on some amateurs who can actually, at the last minute, target that particular asteroid and get some more data on its position, and then we fold that into our orbit, and that improves the orbit. But the other part of your question is, what do you do as a young person in school and all of that? And of course, in my era, things were a little bit different. But you learn as much as you can. I was always interested in this kind of stuff. I like math, for example, but I like math because you could predict the future, with these orbits and stuff like that. So you can't really. So I would say the best thing to do is to get interested, get enthusiastic, learn, and kind of do stuff. And in my case, I got into coding a lot, and coding is a way that you can solve or play around with really interesting problems. And obviously, for computing orbits, coding is really important. You want to be able to solve some pretty sophisticated math problems. You understand the calculus, but if you don't have a coding, a good bunch of people who can do the code and make the computer do the tasks, then you can't make much progress. So getting into all these technical fields is the best thing I can suggest. Always asking questions, always trying to, and for engineers, we solve problems, right? Engineers are kind of the people who look at a problem and they want to know how to solve it. That was kind of the way I was thinking, and then in particular, coding was one way that I could solve the problems I was interested in. So I don't know if that answered your questions, but that's one thing to do. Nowadays, there's all kinds of tools. I'm thinking of MATLAB in particular, that as you get older, you can learn the tools, and MATLAB's a great thing, which didn't exist in my day, where you can play around with mathematics and solve problems and do it kind of in an interactive way. And that's another good example of something to learn. As far as coding, Python nowadays is a good language. So I would encourage people who like to get into this technical stuff, learn Python and just try to solve some simple problems. And it's amazing. It's incredible where it may lead you.
Yeah, I think you gave us probably inadvertently one of the greatest sound bites I've heard in a while, which is I hope the math teachers got it. Why should kids learn math? You will literally learn how to predict the future. That's a great reason to stay motivated in math.
Yeah.
Well, Paul, thank you so much for joining us today. Really appreciate this. Really exciting talk, and uh, I'm really excited to explore the website a little bit. In fact, I'll use this opportunity to kind of pivot towards the JPL education site, some of the activities that we have, and how you guys can, again, kind of engage with this material a little bit more. So if you'll see on my first slide, this is the NASA education webpage, jpl.nasa.gov/edu. And this is where you're going to find all of the activities that my team and I have put together for you on this topic and a multitude of others. Speaking to math on slide 2, you'll see exactly how we construct activities based on this material. This is our kind of our annual Pi Day challenge. And this one is looking at how we sample these types of materials. So this is kind of like a cool challenge for you and your students to explore. Can you figure out the same type of math that Paul and others like him are doing? On slide 3, you'll see other kind of more kitchen type activities that you can do, like making your own impact craters at home, using really basic supplies. All of these rely on very easily accessible materials. So you'll see all types of fields represented: math, engineering, science, and so forth, across all grades in K-12. On slide 4, you'll see that we don't just have activities, we also have written resources for you as well. This one authored by my amazing colleague Lyle Tavernier for the upcoming eclipse. So this is a place for you guys to see a little bit more about what breaking news is coming out of NASA and JPL, and how have we kind of written it for the layman to explore, right? So this can be for you if you want to learn more about these things, or if you are a teacher or you have kids of your own at home. This is a great way to kind of get a primer on all the really amazing topics that are being explored. And then on slide 5, just a reminder, as you saw Paul's website, I really enjoyed as I kind of first started exploring it. The educator in me really liked the kind of simulations and data that I was able to tinker with. So I highly recommend exploring this too, because you get to, it's not just, exploring what Paul's already done, you actually get to play with the models yourself. So I think this is a really cool way to dive a little bit deeper after today's talk. So I'll just kind of close by going to slide 6, which is the teach section. This is where you're going to find all of our activities on the website that are kind of written from the teacher perspective, as you would imagine. These are broken down and lesson planned for you. They have PDFs of student worksheets, answer keys, everything you need to kind of pull a lesson off the shelf and bring it to your students. And this, as you can see from the slide, are broken down that you can filter by subject, grade band, topics, and so forth. Similarly, on slide 7, you'll see that we have a analogous learn section, and this is written more for you to give to students or for you to explore yourself. It's a little more self-driven, exactly the same type of layout, but with a more stepwise approach for you to kind of explore on your own. On slide 8, you'll see that we've bundled some of these activities across all of the things I've shown you today into kind of thematic explorations, whether you want to, kind of take a look more on asteroids and comets, whether you want to build a rover, you want to be an astronaut, and all of these are accompanied by activities, tutorials. We're translating them into Spanish as well. So plenty of ways for you guys to kind of get to the things you're looking for. And lastly, I'm hoping being that you're here with us today, the Teaching Space website on my final slide will kind of put today's talk and pair it with activities and resources for you to explore as well. So everything kind of put together on asteroids and comets that we have, as well as you can see previous recordings and see some of the projects that align to that as well. So tons and tons for you guys to explore. I hope that you'll go back and look at some of these previous videos, explore the website, and take a look at some of the great speakers we've had. And with that, I'll make sure to close up. I'll thank Paul again so much for joining us, and thank you guys for being with us today. I hope you have a great day, and I'm looking forward to seeing you again soon.